In this video, we are going to detail the Michaelis-Menton equation, how we got it, and what we can use it for. So, before we get started, what we need to do is think about the Michaelis-Menton model of enzyme activity. This model states that enzyme plus substrate binds with a relative constant rate and dissociates at a constant rate and forms enzyme-substrate complex. We then have a catalytic constant that turns that substrate into product. This step is the rate-limiting step of an enzymatic reaction. So what we are going to do is we are going to assume the rate of formation is the same as the rate of breakdown. So the rate of formation of ES is the same as the rate of breakdown of ES. When we look at those reaction equations, here is the equation for the rate of formation of ES. Here is the reaction of the breakdown of ES, because there's two ways we can break down ES. We can go dissociate the substrate, or we can turn it into product. So what we're going to do is we're going to pull out the common variable and then what we're going to do is we are going to switch K1 to the other side, and we're also going to divide by the concentration of the enzyme substrate complex. So what we're going to do is we're going to move constants to one side. We're going to move all of the concentrations to the other. When we do that, we get this equation. So we have now put all the constants on one side, put all the concentrations on the other. So let's look at the constants first. If, and in this example, we're going to see K cat is much less than K2. When this happens, you will get K2 over K1. This is Km, or the Michaelis constant. Now let's look over at the concentrations. This concentration of E, draw it over here, is E free, right? The amount of the free enzyme in our reaction. But what we can do, because we know that the enzyme total is equal to the total concentration of the free enzyme plus the concentration of whatever enzyme is bound to substrate. We can do a little bit of rearranging to where we end up with E free is equal to E total minus concentration of ES. So what we're going to do is we're going to plug this back in to E free, so when we do that, we get this equation. E total minus ES multiply those, We still have the concentration of substrate. And that is going to equal Km. Remember, we had K2 divided by K1. When we have that, K2 divided by K1, that is equal to Km. So now what are we going to do is we're going to switch Km and ES. We can multiply by ES by both sides and then divide by Km. But really what we're doing is we're going to just switch them. So we get E total minus ES times S divided by Km is equal to enzyme substrate concentration. Now, I'm not going to show you the next 4 steps. So there's 4 steps that get us from this equation to this equation. Feel free, if you would like, to look them up, but they are not important. And we get left with this equation, like what we saw in class. Now what I'm going to do, because we have yet to bring back kcat, kcat's still important. And so what we're going to do is we're going to multiply everything by that kcat. So now we have this equation times kcat, and when we multiply it through, we get this equation. And like what we said in class and what we saw in class, this is the same as velocity, this is Vmax, and then this stays the same. And we said this is the Michaelis-Menton Equation. And so we said the Michaelis-Menton Equation is very important for what we're going to do. It helps describe the hyperbolic curve that we see on the Michaelis-Menton graph, and that we reach saturation. So remember, the equation is... So we can also tell other things from this graph, and like what we covered in class, and this will be just a review, when Km is equal to S, velocity is equal to 1/2 Vmax. And so remember, here's the Vmax, take 1/2, you drop it down, there is Km. And so when we look at this, the data from our cells, from what we see in living systems, is that they try to maintain a delta, or a concentration of S divided by Km as 1. And what that does is we can look at the Km of an enzyme and we can calculate the cellular substrate concentration, or the body can actually use this ratio to fine-tune enzymatic activity. And then we looked at what happens when Km is much greater than S. Much greater than S. So we reorganized a little bit of our equation, and what we got was V is equal to Vmax times Km times the substrate concentration. And the reason is because if Km is much bigger than S, all we're going to see is Km. The amount of S will be negligible, and so what we have is Vmax times S over Km, and all I did was just move the Km under the Vmax and pulled out the S. And so previously we saw that Vmax is equal to kcat times enzyme total. So what we can do is we can put kcat times enzyme total into the Michaelis-Menton equation, And like we did in the previous step, we're just going to move this out, and we're going to put kcat over km. Times E total concentration of substrate. And what we said was this right here. Kcat divided by Km is known as the specificity constant, and it's a way to compare enzymes. And if you get up to about 10 to the 8th or 10 to the 9th specificity constant, you're approaching the diffusion rate, to where once an enzyme once a substrate reaches an enzyme, it will automatically catalyze it. And we talked about catalase and carbonic anhydrase as an example of those two. What we also said, one last thing we talked about, so we looked at when Km is equal to S. We looked at when Km is much greater than S. Now what happens when Km is much less than the concentration of S? If we look at our Michaelis-Menton equation, or our graph, when Km is much less than S, we are out here at saturation, where velocity is equal to Vmax. And so that's actually how we measure enzyme velocity, is we just overload the system with substrate and we measure Vmax. So, we can also do one more thing with the Michaelis-Menton equation, and we can decide what kcat is, or what the turnover number is for an enzyme. And so that's Vmax is equal to kcat times E total. And so what we want to do is we'll just solve for kcat, which is equal to Vmax divided by total amount of enzyme. And so if on an exam I were to give you the total amount of an enzyme or total concentration and the maximal velocity, you should be able to calculate how many molecules per second that this enzyme can turn it over. And then when we find that, if we do 1 over kcat, and that gives us how many seconds per molecule the enzyme spends. And so for something like carbonic anhydrase, which we said is catalytically perfect, it spends about 1.7 microseconds per molecule doing its chemistry. But in class we had mentioned trying to find Vmax from that curve is not as precise as it could be. And so what we can do is we can take the double reciprocal of our Michaelis-Menton equation to where we get this. And this is known as the Lineweaver-Burke equation. So the Lineweaver-Burke equation allows us to linearize the Michaelis-Menton graph. And so you always have to be aware of the labels on your x and y axes as well as the units. Units are very important. So we said that the point here with which this line crosses the y-axis is known as 1 over Vmax. A lot more precise than what we can do with a hyperbolic curve. And then we said this point where it crosses the x-axis is 1 over Km. Not only is it 1 over Km, but we have to put a negative number because you cannot have a negative Km. So, why do we care about doing this Lineweaver-Burke plot? The reason why we care is because it helps describe different types of inhibition. So there's 4 types we're going to cover. One is competitive. You're probably familiar with that one. The other one is non-competitive. And then the final one we're going to talk about is mixed type. There is a fourth called uncompetitive, but we're not going to really go into detail on that one. So, competitive inhibition. So in competitive inhibition, the competitor resembles the substrate or its transition state. And so what the equation looks like is this. Is that. So this dissociation constant with the inhibitor is known as the Ki. The lower the Ki, or the dissociation constant of an inhibitor, the better. So usually some of the drugs we use have nanomolar or even micromolar to nanomolar Ki's. And that means they're going to bind tightly to that enzyme. So what does a graph, a Lineweaver-Burke plot, look like if you have a competitive inhibitor? And so what it is let's say the red line here is no inhibitor. And so what we want is we want to do this. As we go up, we're increasing inhibitor. And what's very important is to look at what happens to these, to the Km and to the Vmax. So, a competitive inhibitor, nothing happens to the Vmax. The Vmax and the apparent Vmax is the same. What happens to the Km? So here's the Km of our uninhibited enzyme, and then as we add inhibitor, it moves to the right. The Km of this enzyme does not change, but what's known as the apparent Km, the apparent Km increases. The actual Km does not, but the apparent Km does. What we see in the lab will increase. Now with a competitive inhibitor, the way to get it off is to outcompete it with its substrate. So you just add a bunch more substrate in, you'll be able to limit the effect of that inhibitor. Competitive inhibitors also bind to the active site, so they can tell us that the enzyme usually only binds one substrate, and it can tell you what the active site looks like. So the next type of inhibition we're going to talk about is non-competitive. Non-competitive inhibition is known as allosteric interaction, where your inhibitor can bind at the same time that your substrate is bound and change the binding pocket, and it can also bind outside of the active site. So that equation looks like this. So we're going to start with the same starting point. And the same thing goes with Ki. The lower the Ki, the better of an inhibitor it is. And sometimes, depending on how these things bind, they can have two different Ki's. A Ki when the substrate is not bound, and a Ki when the substrate is bound. So, what does this graph look like? So let's say, in this case, the orange line is no inhibitor. And so what we're going to do is we're going to increase the amount of inhibitor that we add. And so in this case, what changes? The drawing is terrible, but the Km, the apparent Km, does not change. What changes is the apparent Vmax. And so in this case, the apparent Vmax, since the numbers are getting bigger, and we're looking at the reciprocal, the apparent Vmax decreases. Right? So in a competitive, the Km increases, the Vmax does not change. In a non-competitive, the Km does not change, but the apparent Vmax goes down. So then what we can have is what's known as a mixed type inhibitor. And this one resembles both Vmax, a change in Vmax, so a non-competitive, and a change as a competitive, so you see a change in Km. So, and the reaction will look very similar to that of the non-competitive graph. So what does this one look like? So again, the red line is the normal. We're going to increase the inhibitor. And so they cross outside of either the Km or the Vmax. So the apparent Km is increasing, like what you saw with a competitive inhibitor. At the same time, apparent Vmax is decreasing, like you saw with a non-competitive inhibitor. So this is why it's a mixed type inhibitor. It looks like a competitive, and it also looks like a non-competitive. There's one other type of inhibitor. So the three that we talked about previously, competitive, non-competitive, and mixed type, those are all known as reversible inhibitors, that the inhibitor can be removed from the active site of the protein. There is a type of inhibitor, let me rewrite that, known as irreversible. And so what happens is, we have our enzyme, we add our inhibitor, and you get this. This complex cannot dissociate. The half-time for this complex can be in the months, until the body can recycle the protein. If we looked at the Michaelis-Menton graph of this type of inhibitor, we'd have our normal untreated, and then let's treat it with an inhibitor. It would look like this, and it would just die. So things like penicillin, beta-lactams, that type of family, are irreversible inhibitors. A lot of our antibiotics are irreversible inhibitors. So I hope this clears up some maybe cloudiness in Michaelis-Menton and as well as Lineweaver-Burke, and it gives you a little bit more insight on why we use Lineweaver-Burke.